Cog Explorer is a framework for contextual robotic exploration. Questions about the environment are generated by an LLM. Corresponding answers are generated using a multimodal VQA model. From the descriptions, an LLM generates a set of object labels. The set of labels is given to an open vocabulary object detection pipeline based on YOLO World. The robot gathers a list of navigable points from a graph of an onboard RRT-based planner. Our results show that Cog Explorer outperformed a state-of-the-art heuristic-based planner.
For effective interactions in the open world, robots should understand how interactions with objects help them towards their goal. We developed a method for affordance detection, where action, object, and effect are all open vocabulary, leveraging a dialogue of foundation models. We show that it produces tailored outputs based on different robot embodiment types and intended effect descriptions. We show the added value of using physical properties of objects and how fine-tuning a VLM can improve on this.
How do you solve multi-step tasks robustly, such as transporting some marbles to the left bowl? BC-style methods use unsegmented demonstrations to learn policies that, however, lack replanable discrete abstractions, therefore they require pre-built sensors to check motion constraints. An alternative approach is to use large language model to generate a discrete plan, which however lack physical grounding. Therefore, in this work, we ask you if we can learn grounding classifier to fix these two challenges. Please check out poster at the grounding language plans in demonstrations. Thank you.
This is the summary video of our work, Dialogue-Based Skill and Task Learning for Robots. In this work, we create a framework that enables robots to continually learn novel tasks and skills from natural interactions with human users, such as dialogues and demonstrations. The robot directly executes the task when it possesses the skill to perform the task. Otherwise, it actively interacts with the human users to learn the unknown skill.
We present RAM, Retrieval-Based Affordance Transfer for Generalizable Zero-Shot Robotic Manipulation. We build an affordance memory from diverse demonstrations. RAM retrieves the most similar demonstration based on language and observation, transfers the 2D affordance to 3D, and enables execution using standard grasp generators and motion planners. Extensive experiments demonstrate RAM's capability of zero-shot manipulation, one-shot visual imitation, and LLM-VLM integration.
Hi everyone, we applied goal modeling techniques from software engineering to robotic planning. Specifically, we reframed the problem of decomposing a high-level task into low-level actionable steps into one of generating a refinement graph of achievement subgoals given a root-level goal. Prior research demonstrated that large language models can be used to make enactable goal-driven decisions, although there was a considerable drop in correctness. We were interested in increasing the correctness of robotic plans generated by large language models. Stop by and we can discuss more.
we present MoMA LLM that grounds natural language instructions in scene graphs for high-level reasoning and mobile manipulation. To do so, we explore unseen dynamic environments that are represented as open-set 3D scene graphs. Given a natural language instruction, we employ a high-level policy for performing zero-shot interactive object search through mobile manipulation. This allows solving complex interactive household tasks within dynamic environments in the real world. As part of this work, we release the task definition as well as code.
Despite recent progress in natural language-grounded indoor navigation, this task remains challenging due to the spatial reasoning and fine-grained semantic understanding required. To address the challenge, we curate the largest real-world dataset for vision and language-guided action in 3D scenes, which we call VLA3D. Our dataset contains over 11,000 scanned indoor rooms from a diverse set of existing datasets. It also contains 23.5 heuristically generated spatial relations and 9.7 million synthetically generated language statements. For each scene, we release Process 3D Point Clouds, Semantic Object and Room Annotations, Scene Graph of Spatial Relations, Annotations for Navigable Free Space, and Object Referential Language Statements. With these features combined, we aim to aid the downstream task of navigation, especially on real-world systems where some level of robustness to changing scenes or imperfect language is often required.
My name is Aaron Lohner from Carnegie Mellon University. The goal of this work is to recognize different types of traffic accidents to help prevent them. To do this, we use scene graphs aligned with vision and language modalities. Our system takes a text caption and video as input, and sampled frames are used to generate scene graphs. Embeddings from the graph, video, and text modalities are aligned within a contrastively trained model, and a prediction is made for the accident class. The added signal from the scene graph modality boosts system performance by over 3%.